And so this is the pressure molar volume sort of plot we would expect to see if we went out and did a measurement on a fluid in a piston cylinder device. But of course, in engineering, what we want to be able to do is we want to be able to quantify, these sort of curves, and we want to be able to predict these sort of curves for, any sort of chemical that we're dealing with. Okay, and so the way we do this is we're going to do it through our equations of states. Okay, all right, and so let's consider a couple of different equations of states and see, if they're able to recreate this sort of pressure versus volume curves that we would expect from experiment. And so if we're dealing with an ideal gas, our equation of state, as you know, is just pressure is equal to RT over V. Right? And so with the ideal gas equation, it's just inversely, the pressure is just inversely proportional to molar volume. Okay? So if we did pressure versus volume, if we were at some T below Tc, and we tried plotting pressure versus molar volume, what we would see is we wouldn't get the sort of features that we would expect from experiment. But basically from this equation, as we decrease volume, we would just see a continuous increase in pressure, right? And we would see that at all the temperatures that we looked at. By changing temperature, all it would do to the curve is it would just shift it up, right? And so that's what we see from the math. So T greater than Tc, Tc, and T less than Tc. And so the point I want to make here is that the ideal gas model for studying phase changes doesn't work at all, right? So our ideal gas model can't predict phase changes. Okay? So for studying phase behavior, ideal gas model is completely useless. Let's now consider another equation of state, the van der Waals gas equation of state, or the van der Waals fluid equation of state, I should say. And so for van der Waals, pressure is equal to RT over V minus B minus A over V squared. Okay? And so with the van der Waals term, we have this first term that kind of looks like the ideal gas term, but the second term here is our attraction term. Right? And so with the van der Waals equation, if we're at a really, really high temperature, so let's say a temperature above Tc, this first term would dominate the equation. Okay? So at high T, or I'll just say at T much greater than or above Tc, the van der Waals can be just approximated as RT over molar V minus B, right? And so in this case, we would expect to see that as we decrease volume, we would just see a continuous change in pressure. So if we plot it like this, P molar V, at T high, we would just expect to see something like this. So T above Tc. Okay? But if we're at temperatures that are comparable to Tc, or that are at Tc or below, then both of these terms in the van der Waals equation become important. Okay? Right? And so what we would see is that here, as we decrease volume, this term would increase, But as we decrease volume, this term, because it's v squared on the bottom, it would increase even further, right? And so at Tc, we would expect with the van der Waals to get that inflection point, so here. And then when we're at very low temperatures, what we'd expect, because we're using a mathematical model, we wouldn't see a discontinuous step change, but what we would see would be something like this. So in the blue, at T less than Tc, we would expect to see something like this. Let me draw that better. Okay. All right, and so what we see is this sort of these minimum and maximum features in the curve. Okay. And so for the maximum in the curve here, the pressure at which that occurs, I'm just going to call that P top. Okay. And the pressure that corresponds to this minimum here, I'm going to call this P bottom. Okay. I'm calling them P top and P bottom. They don't necessarily have any physical, or they don't have any physical significance. I'm just calling them that because they're features in the plot, right? And between P top and P bottom in this pressure range here, we see that there are multiple pressures, or there are pressure values in which correspond to different molar volumes as well, right? And so that's, if we go back to the experimental data, that's what we would want to see. We would want to see some sort of pressure that corresponds to two different volume values. Okay? All right? And so what I mean by that is there is some pressure value, P sat, in which the volumes it corresponds to are the vapor molar volume and the liquid molar volume. Okay? But between P top and P bottom, you can see that there are a lot of pressure values that correspond to multiple volume values. Okay? And so that begs the question, which pressure is P sat? Okay? How do we determine which pressure actually corresponds to the P sat for a given temperature? Okay? And so in order to figure that out, what we need to do is we need to go back to our equilibrium criterion. Okay? And so the first thing I'll say is that for a given pressure between P bottom and this P top that I refer to here and here, we see that from the model for a given pressure, we would see that pressure corresponds to three different volume values. Okay? So the lowest volume value, we would say that would correspond to the liquid molar volume. So the one here. For the highest volume value, we would say that corresponds to the vapor molar volume, so this one. And this middle volume, the one here, that corresponds to what we call an unstable value. Right? And it's actually a molar volume that the system cannot actually attain. Okay? All right? And so that's what the three different volumes correspond to. And so if we're trying to figure out which pressure is Psat, we would have to identify different criteria in which our vapor and our liquid phases coexist. Okay? And so the criteria that determine whether the vapor and liquid actually can coexist with one another, they're going to be the same criteria that we've discussed before. And so in order for the vapor and liquid phases to be stable and coexist, each of the phases has to have an equal temperature. The pressure of both of the phases needs to be equal. And so the pressure, which is a function of temperature and molar volume, if we plugged in the liquid molar volume value, that would have to be equal to the pressure we would get if we plugged in the vapor molar volume value. Okay? So that's the second criterion. And then the third criterion would be that the molar Gibbs energy that we have for the liquid molar volume, that would have to be equal to the molar Gibbs energy we get when we plug in the vapor molar volume into the Gibbs equation. All right, and so another way of saying that is GV minus GL has to be, and so delta G, that has to be equal to 0. Okay? All right, and so these three criterion, these are the ones that we mentioned before. Not only does the system, the system can't just have one of these things be true and then be at equilibrium. All of these things have to be true in order for us to get stable liquid and vapor phases.